Okay, thank you for coming back again. So in this episode, we'll be talking about general topology. General topology is the first step in what many consider to be the real mathematics. And I'm not saying that integration or basic algebra is easy, but general topology is quite something. So, what's the idea of general topology? Today, we're not going into details, but only giving you the idea. So, let's think about what is the first thing that we learn in calculus. That is let's say, the limit. That's the thing. So, what does the limit say? Let's say xn converges to x. If and only if for large enough n x and x can be arbitrarily close. Oh, this is terrible, this handwriting. So this is the thing that we define. Let's look at this. So this is something that we define. I intentionally left something out. So the first thing is for large enough. This is the first thing that I actually left out. And we will come back to that later on, but that's not very important. The very important thing is this. They arbitrarily close. So basically, if you want to define a limit, then you have to define what it means to be a large enough and what it to be arbitrarily close. So the first idea of define what is an arbitrarily close is to define a distance, right? Let's say a distance is basically a function that measures two elements. And then it satisfies something. For example, it should be satisfying that if the distance between x and y is 0, then x equal to y. And it should satisfy this triangle inequality, all these things. And unfortunately, let's talk about a very interesting but seem very simple case, but which cannot be really metrizable. That is convergence by single point. So if we remember that, we say that a function converges pointwise to another function if, let's say, this function given a point x, let's say, we wait for it long enough for it to converge to it. So let's say we have fxn, this is a function, and we have x. We just need this to happen for all x. Well, pretty easy. But the problem here is that if it's very general, then actually when we define large enough, this n doesn't have to be the same. So if we recall, another one is the uniform convergence. It's basically saying that what will come to 0 is the sup, let's say, the distance between fn x and fx will converge to 0. The supreme is taken over x. So basically we are looking at the worst scenario. So this is converges pointwise, this is something else. But this one is obviously metrizable, but this part is not. So that's very, very unfortunate. So we cannot use metric here. So we have to go back. So what exactly do we need? Actually, what we only need is a sense of neighborhood. That's the only thing that we really need to define a convergence. We want a close enough. We don't really need to measure how close in terms of number, but we only need to measure, say, they are close enough by certain means. And also, as we have analyzed, topology aims to somehow create something that is, say, similar to real numbers, and so it will mimic something like the open intervals there, and that's the basic idea of topology. And so we might be a little bit interested into what this can do. Well, it can do quite a lot. So there are lots of topological properties. In general, we will be interested in functional space, so a collection of functions. And as we have analyzed, a collection of functions is not the same as the collection of real numbers because, well, they're not the same, simply that. Take or given. So we cannot expect them to have very nice property by the moment. But still, there are quite a lot of really nice things that we can have for topological spaces by adding on some of the properties. And here is the one that actually will be interested in talking about. So let's talk about this. So the first property that is very interesting is called let's call it the separability. Well, this is not a quite well defined term, but it's basically because it can mean two things. It can mean quite a lot of things. It can mean either you can separate points, which is the thing that we use, or it can be countable in some way. So that's the thing that we'll be talking about. So separability, so let's talk about this. So let's say we have a sequence of x, and this is our sequence. And we want it to converge to this x and x, and converge to y. And if this happens, we actually really want them to be equal. So we don't have xn converge to x and xn converge to y, but x and y is not equal, then how can you really define any limit? So to ensure that, basically what you need is so-called Hausdorff property. And then there's a huge number of it they're available, including, for example, all these things separating to open set, separating a lot of things. So these can be quite useful, actually. So this is the one thing that we will be interested in, the separability. Another thing that is we will probably briefly mention is countability. So basically, we are interested in having something that's countable. Not to spell anything, but to have something that is countable is actually quite useful, because, especially for probability, because we want something to be measurable, and to be measurable means we can actually in some way define probability, and we need it to be countable, meaning that it's as many as natural numbers but not as many as real numbers. So we do need that, and that's something that is very interesting. And then we have this most important part, that is we call compactness. So this is probably the most interesting part of topology, actually. So what compactness means is it has many identical definitions, but it's probably, in my opinion, the most powerful properties that you can have in topology. And actually it happens a lot. So what is compactness? So let me give you an example of why it is very important. So let's talk about a number, a thing about, let's go back to the real line. So let's talk about, say, a real number from 0 to 1. There is a very interesting thing here. So if you recall from calculus, if you don't, that doesn't matter. A fact is, if you have a sequence here, if you have a sequence in there, it always have a convergent subsequence. So why does this interest us? Because this actually solves a very important problem. So how do we prove something converges to something? Well, we have to do two things. So let's say first we need to prove that it actually converges, doesn't diverge. Okay? And then we need to show that if it converges, it indeed converges to the thing that we want it to converge to. So that's the other part. Now, if we have this compactness, why this is helpful? Let's give something like this. Let's draw this. Let's say we have this. My claim is that actually what you need to do is only the second part. So basically you need to show any converged subsequence will have a further subsequence that converges to the same point. So why? Think about this thing. Does it converge? No, of course it always converges. So why doesn't it converge? So one way to show that is to show here, here. Let's say it always go here and this again. So this sequence have a convergent subsequence. It will converge to, for example, here. And then we can also take this subsequence here, and then converge here. So they do not converge to the same point, and so it doesn't converge. But and if you use as a, this is left as an exercise, if you use some kind of work, then you can see that if you can prove that all the subsequence, because this compactness, all the sequences have convergent subsequence, you actually can use concrete argument to show that as long as you prove that it's compact and converge to the same thing, then everything is fine. And this is only a part of the compactness. So it is very interesting. In any case, this is what we'll be talking about in next class. So thank you very much and see you next time.